Last week, a couple of you sent PM to me asked to talk more about the convolutional sequence-to-sequence model that I mentioned in the last video. So in this video, I will elaborate more on the paper Convolutional Sequence-to-Sequence Learning, published by Facebook last year. This video will show you the detail of the neural net structure as well as the training and generating procedures. If you want to know more about these things, then keep watching. Hey guys, welcome to Steve TV. I'm Steve, a data scientist and Kaggle competitions master. Now, if you are new to me or my channel, we talk about everything deep learning in computer vision, natural language processing, and recommender system. In this channel, we review some recently published great and interesting deep learning papers. So if you want to learn some state-of-the-art deep learning techniques, make sure you join me by hitting that subscribe button below. Let's start talking about the neural net architecture. This graph gives you an overview of what the model looks like in training time. You might wonder, why do I mention training time? Isn't the model supposed to be the same during training and testing? I'll go over that in just a few minutes. The top shows the encoder and the bottom shows the decoder, which share the same structure. They are both composed of blocks of convolutional layers with gated linear units. Again, this figure shows only one block for simplicity. The middle part is an attention function. If you don't know what gated linear units and attention are, click the eye icon in the top right corner. My last video has explained these two concepts. The paper applies residual connection between blocks in both the encoder and the decoder, which allows for deeper convolutional network. But why does residual connection work? When you stack up convolutional layers to form a deeper model, it becomes harder and harder to optimize since the model has a lot of parameters, resulting in poor performance. You might think that, could we that deeper model to perform at least on par with the shallower ones? So researchers propose a solution, that is to add the previous block's output onto the current block's one. Instead of trying to approximate the direct mapping function h of x from the input to the output, we're now estimating the residual mapping function f of x, which is essentially h of x minus the input of the current block. You can think of f of x as modifying x to approximate h of x, instead of learning a whole new mapping function. This technique makes the learning process easier, enabling the model to go deeper. In addition, recall that in the last video, I mentioned that for the attention function, the query is the decoder hidden context representation, while the keys and the values are the encoder hidden states. In fact, they propose to separate values from the keys by adding the embedding vectors of the source onto the encoder hidden states. Empirically, they found that this separation boosted the performance of the model. Okay, now that you understand the detail of the model architecture, let's talk about how the model is being trained. In this figure, the goal is to translate from English to German. The English words are fed to the encoder to compute the keys and the values for the attention, while the German ones are processed by a decoder for generating the next word, given a target in the previous time step and the English input. Note that for encoder, the input sequence is padded so that the input and the output lengths are the same. For decoder, the padding makes sure the target of the decoder is shifted by one word from its input. Because we have the decoder target output in the training time, the attention in the middle can be computed simultaneously for these four queries. In this way, the training process can be fully parallelized. However, this is not possible in test time, since we need to wait for the next word to be generated in order to proceed to the next time step. That's why I say that this graph illustrates the model in training time earlier in this video. In this example, the decoder has 4 pairs of training samples. For each training sample, the model predicts the next word given a sequence of previous target outputs and a source input. So the input of the first sample is padding, and starting tag. The decoder should generate Z, which is the German word for day. So that is how the training is done. Let's move on to discuss how the model generates sequences. Since we don't have the ground truth output label, we have to generate one word at each time step and use that word as the input for the next time step. This animation demonstrates the generating procedure. When a new word is generated, the convolutional kernel slides to the right by one word to process the newly generated word. In addition, They also use a technique called bin search, which generates a couple of hypotheses and select the best one. Let's say we have bin size equals 2. At each generating time step, we pick the top 2 most likely predicted words, each of which then form a tree-like structure of hypotheses. The final output will be the sequence with the strongest confidence. Alright, so you have learned the detail of the convolutional sequence-to-sequence model, how it is trained, and how it generates sequences. Now I'm gonna tell you a bad news of myself. That is, I'm joining Taiwanese Army next week for 4 months, which implies that during this period I cannot post videos on a weekly basis. However, I'll try my best to at least upload a paper review video every month. So if you haven't subscribed yet, make sure you hit that subscribe button below so you don't miss out. And if you have any question or comment, go ahead and put it in the comment section below. Thank you for watching. I'll see you in the next one.